Hi everyone, and welcome to the first of 4 videos where we're going to be looking at some past exam questions on the topic of orders of reaction and rate equations. We see we've got this question here. This is very standard. This is actually a question from the old OCR specification, but it's very standard of the type of question that you'd get on the new specification as well. We've got here our equation, and we've got some experiments and some data here in a table. And what it's asking us to do is to work out the rate equation and also the rate constant. Okay, and actually this sentence here is quite important, where it says, in your answer, you should make clear how your conclusions fit with the experimental results. That's something that students often miss out, and they do often give you credit for that. So we want to make sure that we spell that out. So if we want to work out the rate equation, before we do that, the first thing we're going to need to be able to do is to work out what the orders of reaction are with respect to each of the two reactants. And to do that, we need to look at the experimental data, and we want to see what effect changing the concentration has on the rate of reaction. And so to be able to work that out, what we're looking for is to find two experiments where only one of the concentrations has been changed. Okay, so for example, if we look at experiments 1 and 2, you can see that the concentration of NO2 has changed, but the concentration of the O3 has stayed the same. And so therefore, whatever's happened to the rate has been a consequence of the change in the concentration of NO2. And so that's how we're going to start. We're going to start with looking at these two experiments. And we're going to make this clear in our answer, as we've said. So we're going to say, from experiments 1 and 2, and then we're going to look at what's gone on with the concentration of NO2. And if you can't tell just from looking at it, you can work this out on the calculator. You can say, right, what is the concentration in the second experiment? 0.00225 divided by 0.0015. And that comes out as 1.5. So going from experiments 1 and 2, the concentration of NO2 has been multiplied by 1.5. Okay. And we then need to think what has happened to the rate. And so we're going to do the same thing here. We're going to divide the rate in the second experiment by the rate in the first experiment. Okay. So we're going to say 7.2 times 10 to the power of minus 8 divided by 4.8 times 10 to the power of minus 8. And that also comes out as 1.5. So what does that tell us? Well, if the concentration of NO2 has been multiplied by 1.5, and the rate has also multiplied by 1.5, then the two are directly proportional to each other. Okay, or in other words, the order with respect to the NO2 is first order. And changing the concentration has a directly proportional effect on the rate. Then we want to do the same thing, but for the O3. So we want to find two experiments where the concentration of O3 has changed, but the concentration of NO2 has stayed the same. Okay. So we already looked at experiments 1 and 2, didn't we? And we said this had times by 1.5 and the rate had times by 1.5. So we then want to find one where the NO2 is not changing. So we want to look at experiments 2 and 3 here. So we say, look, that's staying the same and only this is changing. So we can see here, hopefully you can see this, that the concentration of O3 has doubled here. Okay, that's been multiplied by 2. And then we want to see what effect has it had on the rate. And again, this might not be so obvious. Again, watch out that the power of 10 has changed, which you need to be a little bit careful of. So if you can't see that clearly, again, we can just divide it. So we can say 1.44 times 10 to the power of minus 7 divided by 7.2 times 10 to the power of minus 8. And that also comes out as 2. So therefore we can write our conclusions about the O3. Again, we want to make sure we're linking it to the experiments. So we're saying from experiments 2 and 3, then the concentration of O3 is multiplied by 2, and the rate is also multiplied by 2. So again, they've changed by the same factor. So therefore, the order with respect to the O3 is also first order. Okay, now that we know the orders of reaction, we can write our rate equation. Okay, rate equations are always in the same format. Okay, it's always the rate is equal to the rate constant and then multiplied by the concentrations of the reactants, and each reactant is raised to the power of the order of reaction. Okay, these are both first order, so the concentrations are both to the power of 1 in the equation. Right, the last part that we need to do then is to work out what the rate constant is. And so that involves rearranging this equation. Okay, we want to work out the rate constant K. So the rate constant K is going to be equal to the rate divided by the concentrations. Okay. And that will be the same in any of these questions. It's always going to end up as the rate divided by the concentrations to their respective powers. And so all we need to do now to calculate the rate constant K is to actually put some numbers in here. So we're going to use the data from the table that we have. It doesn't matter which experiment we choose, okay, as long as we pick all the data from the same experiment. The idea is the rate constant is a constant, so it should give us the same value regardless of which experiment we choose. Okay, so I'm just going to choose experiment 1, and we're just going to substitute the values in. So the rate is 4.8 times 10 to the minus 8, and the concentration of NO2 is 0.0015, and the concentration of O3 is 0.0025. And in this case, both of these are first order, so we don't need to square them or anything like that, but do watch out for that. If you've got one that's second order, for example, you'd need to make sure you've squared the number here. And so then let's just go ahead and calculate that. Times 0.025. And we end up with a value of 0.0128. Now that's fine, and it doesn't tell us to do anything else here. It seems like we've finished the question, but we never ever want to write numbers without units. Okay, and I think it's a bit bad that sometimes they don't actually explicitly say that they want you to calculate the units, but they always do. So we do need to work out what the units are going to be here. We need to get in the habit of not writing down numbers without units. We always need to be writing some units. Okay. And to work out the units, all we need to do is substitute the units into the expression instead of substituting the values in. Okay. So the units for rate of reaction are moles per decimeter cubed per second, and the units of concentration are moles per decimeter cubed. You can then see that we've got moles per decimeter cubed on both the top and the bottom, so we can cancel that out. And we can say that it's second to the minus 1 over moles per decimeter cubed. And then we can use a bit of a trick of maths here where we're saying if we've got something on the bottom of a fraction, then it's the same as being to a negative power. So we can then convert this into seconds to the minus 1 and moles per decimeter cubed to the power of minus 1. And then finally, we just need to sort this bracket out, and we're going to call this seconds to the minus 1, moles to the minus 1. And then if you end up with a situation with a power inside the bracket and outside, you multiply these powers. So minus 3 multiplied by minus 1 is positive 3. Then if you leave it like that, that's absolutely fine. But the standard way of writing it is to write it with the positive 1 first. So we'd say this is decimeters to the power of 3, moles to the minus 1, seconds to the minus 1. And there we go. We've worked out our rate equation. We've worked out our rate constant and the units. And we've shown clearly how our conclusions fit with the experimental data.